All right, so let's have a look. Sigma notation is basically just a mathematical way to say find the sum of. So rather than me typing out or the teacher typing out, determine the sum of the series, blah, 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 we use sigma notation. So just to start us off, we need to actually understand all the different parts of the sigma notation that we work with. And there's three that we need to, I suppose four that we need to know. So the first one is the actual sigma. So this symbol over here is our sigma. And sigma means sum of. So that is saying add together or find the sum of. It's basically like a sideways M. You'll see when I draw it a bit later, that's kind of how I draw it. Your sigma doesn't have to be perfect. A sideways M is perfectly fine when you are needing to write sigma. So that's the first part, sum of. And then there's three other bits of information that we need to know. The first bit of information is going to be the value down at the bottom. Now this will generally have a variable. So let's say M, I've now gone M equals, let's say 1. And this is telling me what is the first term in the series that I'm adding. So if M is equal 1, I'm saying I'm adding from term 1 all the way up to whatever it is that we're going to add up to. And what we're going to add up to is given to me by this top number. So if this was, say, for example, 12, what I'm saying here is that I am adding terms 1 to 12 of a specific sequence or series that we're working with. So those top and bottom numbers tell you how many terms and which terms you are adding in the sum. The next bit of information that we're given is this bad boy over here. It will always be on the right hand side of sigma, and this is your general rule, or what we call the nth term. So this will tell you what type of series you're working with. Is it geometric? Is it arithmetic? It will give you the specific TN formula so that you know exactly what the rule is. And yeah, it's essentially telling you what pattern are you working with. I'll come to the bottom block in a second. So if we have a look at an example here on the side, this is an example of a sigma notation that we would need to understand. So remember, all this is maths, language, so translation from English to maths. That is all this is. So if we go and have a look at what we've been given, we have been given k equals 1, so that's where I start. So we are adding terms, we're starting at 1, and we're ending, we look at the number on top, so terms 1 to 4 of the series 4k minus 1. Now that's an arithmetic series. And knowing what type of series it is, so like I said, it tells us what type of series we're working with. Knowing what type of series it is allows us to figure out which sum formula we're going to work with. If it's arithmetic, we have to use the arithmetic sum formula. If it's geometric, the geometric sum formula. If it's a sum to infinity question, the sum to infinity formula. So that bit of information, this general rule, gives us a lot that we need to sort of use when we answer questions. So that is what a sigma situation means to us. Which terms am I adding? What type of series am I working with? Now, it's really easy to work with this if we start from the first term and we go to the fourth term, because then we know we're adding 4 terms. Term 1, term 2, term 3, term 4. Nothing super tricky. You're going to see in some of the examples a bit later that we don't always start by adding from term 1. We might start adding from term 3 or term 7 or whatever. We don't always start at term 1. And that can then be a bit tricky to figure out how many terms we are actually adding. Now, I'll explain this a little bit more when we get to those examples. But this little formula down at the bottom in this block over here allows us to figure out how many terms are in this series, so how many terms we're adding. All we do is we take the top number. So if I have a look at this example here, it would be 4 minus the bottom number, which is 1, and we add 1. So in this case, we're adding 4 terms, and we saw that term 1, term 2, term 3, term 4. Nice and easy. Nothing too stressful there. Like I said, this little formula is going to be way more useful when we're not adding from the first term, but we're going to have a look at some examples in a few minutes when we get there. But this is what sigma is. This is what sigma is saying to you. It is not something that we need to get stressed about because, like I say, it really is easy. We just need to understand what it's saying to us. So I'm going to wait there in case you want to take a screenshot, but otherwise we're going to have a look at some examples of firstly converting a series into sigma and then actually working with the sigma notation and finding the sum. So guys, the first two examples that we're going to look at of taking a series and putting it into sigma form, it's not something that we ask a lot. Like we definitely can ask it, but it's not something we ask a huge amount of. But if you can convert between the two, it does help you understand what sigma is saying to you. All right. So if we now have a look at this first example here, I want us to write the following series in sigma notation. Now remember, for sigma notation, we have to know what term we're starting with, what term we're ending with, and what is the nth term. So what is the general rule? Now, when you are given a series like this, you will always assume that you are starting to add from term 1 unless they tell you otherwise. So I haven't said anything here, so we're adding from term 1. So we're adding 1, 2, 3, 4, 5, 6 terms. So that's great. I already have my top and bottom numbers of sigma. So if I want to fill that in straight away, I can do that. So I already know that sigma is, let's just go n equals 1. You can use any variable you want. It really doesn't matter. It must just match up with your nth term. I'm going to use n all the way up to term 6. Sorted. I've got 2 of my 3 parts of my sigma that I need. The next part I need is that nth term. Remember, to the right of sigma, we have our general rule or the nth term. So we need to go and figure out what the pattern is here. Now we know how to do this. We've been doing this since like grade 8, grade 9. This is not a tricky situation, but we obviously need to know what type of series I'm working with. So we go back to our series and we figure out what's happening. 3 to 5 is an addition of 2. 5 to 7 is an addition of 2. 7 to 9 is an addition of 2. We can keep going, but it's really not necessary. What we see is that we have this first difference, and so what we have is an arithmetic series. Help if I could spell series. Okay, because we know that, we know what Tn formula to use. Because remember, depending on the series, we have different Tn and Sn formulas. So for arithmetic, it's a plus n minus 1d. We know what a is because we were given it. It's 3 plus n minus 1, and we've just worked out our differences 2. Now, guys, I would simplify this because it's just going to look a lot neater when you write it out. So if I distribute this 2 into the bracket, I get 3 plus 2n minus 2. And so Tn is equal to 2n plus 1. And what I've worked out is what I need to put next to sigma, 2n plus 1. Now, obviously, you won't have the box there and all of that, and you know that. But that is essentially all sigma is. Given the rule, what terms am I adding? That's it. It's telling me what I'm adding. So for us to be able to convert between the two is very useful because it just gets us comfortable with what we're working with. I'm just going to write this without the block in case you want that. That's a weird looking sigma. So let's try that again. Like I say, it's a sideways M. Nothing fancier than that. N equals 1 all the way up to 6, 2n plus 1. If you want to put that in brackets, obviously feel free to. So if you want to put brackets around that, that's fine. But that is your general term. And that's sigma. Right, so what I want you to try for me, whoopsie daisies, is question B here. So figure out what type of series you're working with. Go and find your general term and figure out how many terms you're adding. And like I say, we always assume, unless told otherwise, we're starting from term 1. Remember, all I want from you is just write it out in sigma. I don't actually want the sum. I just want to know what the sigma notation would be here. So guys, feel free. Oh, I suppose you can't really write sigma in the chat here. That's asking a bit much. So I'll give you another minute and then we'll have a look at what sigma should look like. Thanks, Faith. That is actually very useful. You can let me know if you're done, guys. Because like I say, for me to ask you to try type sigma on the chat is really mean. So I don't expect that. You can also just give me a thumbs up if you want. Thanks, Artie. Okay, guys, let's have a look. So we're adding 4 terms here. So automatically, I know the top and bottom numbers of my sigma. So the bottom, and I'm just going to use another variable so that you can see what it would look like. Let's say P is equal to 1 all the way up to 4. If you used N, obviously that's absolutely fine, but we do sometimes use different variables and it means the same thing. Okay, remember, variable is just a placeholder for an unknown. Right, the next thing we do need to do though, English, is we need to figure out what type of series this is. Now, be careful, we're not adding the same thing each time, we're not subtracting the same thing each time. What we're actually doing is we have got a constant ratio. So what we're doing each time is we're timesing by 4. And what that means is that we've got a geometric series this time. Now, the Tn formula for a geometric series is Tn is equal to A times R to the power n minus 1. A, we know it's 2. R, we can easily work out by saying term 2 divided by term 1, which is 4. That's why I said we're timesing by 4 each time. So 4 to the power n minus 1. That's our Tn formula. And so when it gets back to sigma, we've got sigma starting at 1 up to 4 of 2 to the power 4. Now here I would have p minus 1 because that's my chosen variable. If you have n minus 1, that's obviously absolutely fine. If you want to put brackets around the 4, that's fine. If you want to put brackets around the whole thing, that's fine. It's not necessary, but it's fine if you would like to. If anything, I'd maybe suggest brackets around your base, but even that is not necessary. You're going to see in the examples they use brackets around the base. That's what I'm saying if you want to, but it's not necessary if you don't want to. And that's it. We've taken our series and we've put it into sigma notation. So grade 12 again, we don't ask this question a lot, maybe more in tests and maybe like your junior exams, your teachers might, but we'll come to finals, we just expect you to know what sigma means. Being able to convert between the two helps you understand what sigma is saying to you. So like I said, you're not going to get lots of questions like this. You probably won't get any questions like this. But if you can do this, you understand what sigma means, and that is good. Okay, so I'm just going to do this in case you didn't get screenshots of those examples. And then we're going to actually have a look at some examples where we now start to find the sum, where we take that sigma, we convert it to what am I adding, and let's go and add that to find a sum. And remember, girls, if you have questions at any point, pop it on the chat, unmute yourself, whatever you're most comfortable with, that's absolutely fine. But please do ask questions, because like I say, this is often the stuff that we get most confused with when it comes to sequences and series. Alrighty. So let's have a look at these examples. So now we're actually wanting to find the sum. Remember, I spoke about this when we did the first sort of lesson on series. The question or the statement evaluate just means find the sum of. So it's asking us to find the sum of the sigma notation that's been given to us. So we're going to break down what we have in order to understand what it is that we're actually doing. And again, because we can write a sigma notation, because we can write a series in sigma notation, we should be fine. So we've got this k equals 1, and we've got this 10 at the top. So what that's saying to me is that we are adding terms 1 to 10. So essentially what I'm doing is I'm adding 10 terms. Now I need to know how many terms I'm adding, because remember, both of our sum formulas, arithmetic or geometric, requires n, an n value. If you're not too sure, remember n is equal to the top number, so 10 minus the bottom number 1 plus 1. That's the additive inverse. -1 plus 1 is 0. So we're adding 10 terms, as I said. So that's the first thing. We're adding 10 terms. The second bit of information we've been given is through our general formula here. So guys, what you should notice is that this general formula is linear. There's no exponent, so it's not like k squared, which means it's not quadratic. We don't actually work with quadratic series. It's not geometric because there's no exponent. It is just a linear expression. So we are working with an arithmetic series. Like I said to you earlier, this is really important to know. I need to know what type of series I'm working with so that I know what sum formula would be appropriate. Now, in this case, our sum formula that is appropriate is S of n is equal to n over 2, 2a plus n minus 1 times the difference. So again, this is on your formula sheet. You don't need to know this. That is not something you need to stress about. But we do need to be able to identify which formula to use so that we've got that. So now we have all of this information, we need to actually go and add. Now, in order for us to add, we need terms. So the first step of any sum or sigma question is to find the first 3 terms. Now, I always say first 3, you can actually just find the first 2 if you want. But I always say first 3 because you get a clear idea of what's going on with the pattern, and there's nothing you need to stress about. So what I want you guys to do is I want you to substitute in k equals 1. I want you to substitute in k equals 2. And I want you to substitute in k equals 3 to find the first 3 terms of the series. And when I say substitute, you're substituting it into the Tn formula. Right, Kanisile, how do we know which type of series it is? Okay, so really good question. I'm going to move this down a smidge so we can do a little summary here. All right, so guys, if you're not too sure how I came to the conclusion that this was an arithmetic series, what we need to remember is that a geometric series has an exponent. So, for example, we had one here of 2 times 4 to the power n minus 1. So this exponent tells me it's geometric. An arithmetic is linear. Now, what I mean by linear is that you just have your variable. There's no exponent attached to it. There is no weird situations going on with it. It's literally just the variable. So an example here would be that 4k minus 1. It's just a linear expression. Quadratic, which we don't really work with in series, but it is useful to know. Quadratic will have n squared. So for example, I don't know, n squared plus 2n minus 3. Remember, it's that an squared plus bn plus c. That is your geometric. So those are sort of the different types of equations or end terms that we work with. And that's how we know which is which. So because this was just a linear expression, I knew that it was arithmetic. I'll scroll back to this now. Over here, because I had this exponent, I knew it was geometric. So that's how we can sort of identify what's what. So can you see that? I hope that makes sense. If not, obviously just let me know. Okay, guys, and obviously you can put your terms in the chat so that I can see that we are substituting correctly. And remember, all you do is you're subbing in. So T1 is equal to 2 times 1 minus 6. So the first term is equal to -4, and you keep going like that. Emmanuel, nice. I agree with all of those terms. I didn't even see I just assumed that take a negative wasn't equals was a negative. Nice. Siba, nice. Right, so guys, what you can hopefully see is that term 1 is -4, term 2 is -2, term 3 is 0. So we have our series that we can now write out as a series, and we know what we're working with. Now that we have this information, we can go and substitute into our sum formula. So your sum formula is there for you in that like turquoisey color. Okay, I can grab my turquoise back. There we go. So S of, now remember we said we're adding 10 terms. So the sum of 10 terms is equal to 10 over 2 times 2 times A. Now remember this value here is your first term. So that's A, -4 plus 10 minus 1 times your difference. Now, there's a couple different ways that you can know what your difference is. Way number 1 is you've already found the pattern. Okay, we've got the pattern here. We found the first 3 terms. So you can see that each time you are adding 2 to get your next term. Alternatively, guys, hopefully what you can see is that the coefficient of your variable is the constant difference. So by looking at your actual nth term, this number in front of k tells me what the constant difference is. So I now know my constant difference here is 2. So I sub that in for D. And then I just put all of that on my calculator and I get what my sum is. So I'll give you a second or two. Tell me what the sum of these 10 terms is. What is the sum of these 10 terms? I've substituted it into the formula for you, so you just need to put it on your calculator. Nice, Kanisile. Nice, Letavo. Ubadani, nice. Okay, so guys, the sum of these first 10 terms is 50. Now that makes sense. Even though the first 2 terms were negative, the rest of my terms are all going to be positive because I just keep adding 2. So it does make sense that my sum is positive because I'm starting from a negative. 10th term is not going to be hugely big, so 50 seems about right. But that's it. Done, sorted, substituted in, no problems. Right, I'll wait in case you need to take a screenshot, but otherwise I'm going to move to example 2. Or example B rather. Okay, so let's see B. So B, we've now got I as our variable, doesn't really matter, it means the same thing. 1 to 8 of 5 times negative 2 to the power I. So back to Kanisile's question earlier, I now know this is geometric. I know this is geometric because of this exponent here. Because I've got an unknown or a variable in my exponent, this tells me that this is a geometric series. Because this is a geometric series, I automatically know what my sum formula is. And again, guys, this is on your formula sheet. S of n is equal to a times r to the power n minus 1 over r minus 1. And that's all coming from just looking at what the nth term is. I also know, because of the top number and the bottom number, that I am adding terms 1 to 8. Now, this isn't too tricky. It means that we're adding 8 terms, but obviously you could say 8 minus 1 plus 1 to get n, but we're adding 8 terms here. So again, the first thing that I'm going to do is I'm going to go find what the value of my first 3 terms are. So I need to substitute I equals 1, I equals 2, and I equals 3 to figure out what term 1, 2, and 3 are. So I'm going to give you a second to quickly find those first 3 terms for me. And then we'll have a look at what we need to do next. And guys, all you're doing is you're substituting I into that Tn formula. That's it. Nice, Siba. Nice, Artsy. I'm going to give you guys another second or two, and then we'll have a look. Okay, so guys, you just substitute in. Term 1 is equal to negative 10. Term 2 is equal to positive 20. Term 3 is equal to negative 14. So we've got our series minus 10 plus 20 minus 40. Whoops. And so we would keep continuing with that series. Now, we do know what R is, because remember, R is the base of your exponent, but sometimes R is represented a bit differently. So for these, I would always recommend just working out what R is using our normal methodology. So R would be equal to term 2 divided by term 1, which is equal to negative 2. So it does match up. So that's not too stressful, but you're going to see in some examples later that it doesn't always look the same as what it actually represents. I'll explain why when we get to those. But it's always a good idea to just work out what R is, just to be 100% certain. And now that you do know what R is, you obviously know what A is, you can go and substitute into your sum formula. Now remember, it's a sum of 8 terms. So that would be A, so negative 10 times R. Now remember, use brackets, because what we need to be careful of is that it's negative 2 to the power 8 minus 1. If we don't put brackets around the negative 2, our calculator is not going to calculate it properly. Okay, all over R minus 1, so negative 2 minus 1. Again, always use brackets when you substitute. It just makes your life easier, and Kirsten taught us this lesson a few lessons ago. Okay, so again, few seconds, tell me what your sum of these 8 terms is. Nice, Ukiswa. Joy, very nice. Kirsten, nice. Okay, guys, exactly. The sum of these 8 terms is 850. Okay, now even though it alternates between positive, negative, your last term is the 8th term, so it's an even term. All of your even terms in the sequence or series are even, which means that that last positive term will be greater than the previous negative term. So it will end up positive once you add and subtract. Alrighty, but again, nothing too complicated. Find the first 3 terms, know what series you're working with, off we go. So I'm going to wait 2 seconds for you to screenshot, and then we're going to have a look at what happens if I'm asking you for the sum of infinity. Nothing changes in our methodology or in our approach. We're just now looking at the sum to infinity. Okay, let's see. So in question C, we've got the sum to infinity from the first term to infinity of 2 times 4 to the power 1 minus r. Now, this is an example where the r value is a little bit different, but we'll deal with that in a second. So first things first, I know that that is a geometric series. There's 2 reasons. Firstly, I've got this exponent, so it's geometric. Also remember, the only sum to infinity that we work with is with geometric series. So this has to be geometric, but the exponent is the dead giveaway. Because it is sum to infinity, remember your SN formula looks a bit different. It's sum of n terms is equal to a over 1 minus r. It's much simplified, much more simplified equation that we work with. So that's what we're dealing with here. And then obviously we have got from term 1 all the way to infinity. So again, what I'd like from you guys is work out term 1, term 2, and term 3 for me. What are the first 3 terms of the specific series? That's nice. Nice, Emmanuel. Okay, guys, so term 1 was 2, then it's a half, then it's an eighth, and so we will keep going. Now, what I want you to remember is when you've got sum to infinity, let's go here. So sum to infinity means that we are working with a converging series, converges onto a single value, And what that means is that our R value has to be between -1 and 1. Now, right now, if I look at my R value, which is my base, it's 4. That makes no sense. That's not within the range, so this can't be converging. But remember, I said sometimes what happens is the way we present our TN formula for you is a little bit different. So if we go here and we work out R would be a half divided by 2, which actually gives us R is equal to a quarter. That makes way more sense. This now fits in with my range that I want, so I'm happy this is actually converging. But then the question is, why in the original do I have a base of 4? Now, if we go and have a look at this exponent, remember your exponential laws. You could break this up. This would be 4 to the power 1 times 4 to the power negative R. Now, remember, guys, that's a fraction. 4 to the power negative R is 1 over 4 to the power R. There's my quarter that I'm talking about. Okay, so all we're doing here is we're just putting it in a different format. Still means the same thing. This negative R implies the fraction. Still means the same thing. It always helps, and this is why I'm saying just double check what your R value is in any case. Even though you've got the equation there for yourself, double check. It's such an easy quick check. Term 2 divided by term 1, and you automatically know what R is. Okay, so now that we're happy this is actually a converging series, we can work out our sum to infinity, which is A. So remember, this first term is A. So 2 over 1 minus that quarter that we've just confirmed. And so our sum to infinity here is equal to 8 over 3, if I'm not mistaken. You can double check me, obviously. But I'm pretty sure it's 8 over 3. Okay, so sum to infinity questions are no different. First 3 terms, figure out what R is, make sure you're happy with everything, sub it into your formula, and work out the sum to infinity. So I'm going to wait in case you want a screenshot, and then we're going to have a look at some examples where we're not starting at the first term in our addition. Okay. So like I said, we're going to have a look at now at some examples where we're not necessarily adding term 1, term 2, term 3, term 4. We might be adding term 3, term 4, term 5, term 6. And so term 3 or term whatever becomes our first term. Right, so let's have a look here. If we have a look at our sigma, we have been told that now k is equal to 3, so we need to be careful here, all the way up to 10. And then we've got our nth term. We'll get to that in a second. So what this is saying to us is that we are adding term 3 to term 10. So I'm not adding term 1, term 2, term 3, etc., etc. I'm adding term 3 to term 10. Now, this is where that n formula is really important. N is equal to 10 minus 3 plus 1. 10 minus 3 is 7 plus 1 is 8. And so I'm adding 8 terms. Now, this is why the formula is so important. Often what we sort of think is, okay, cool, 3 to 10 is 7 terms, 7. But it's not. We forget to include a term. So if you just count it out on your fingers, obviously we won't do it for all of them, but counting it out on your fingers for this one proves why we have to add the 1. We're adding term 3, 4, 5, 6, 7, 8, 9, 10. It is 8 terms. We often forget to count one of those terms when we do the addition or when we do the subtraction, and so we end up calculating the sum of the incorrect number of terms. So these questions are where that top minus bottom plus 1 is really important. Okay, so we know how many terms we're adding. If we now go and have a look at our pattern that we've been given, we can see this is linear because it's just a linear expression. Let's maybe say arithmetic. And so because we know it's arithmetic, we know the formula that we have to use. So our formula is S of n is equal to, and that whole long thing that is on your formula sheet. Right, but our method doesn't change. we're not going to change what we were doing from before. The only thing that sort of becomes more important is working out how many terms, top minus bottom plus 1. We're still going to work out the first 3 terms. What we just now need to be careful of is the fact that my first 3 terms is going to be term 3, term 4, term 5. So I want to substitute in for k equals 3, for k equals 4, and for k equals 5. These are my first 3 terms. Yes, I'm not starting at term 1, but this is the first term that I'm going to add is term 3. So that's what I need to work out. So if I substitute in 3, so term 3 is equal to 5 times 3, which is 15, plus 4, which is 19. Obviously, we keep going. The next term is then 24, if I remember correctly. Yeah. And the next term is 29. So now I know I've got the series 19 plus 24 plus 29, and so on all the way up to the 10th term. So nothing has changed in what we do. We still substitute in to find the first 3 terms. We now just need to be very careful of where we start. But I've got all of this information, so I can substitute into my sum formula, exactly as what I did earlier. So the sum of, remember, it's now 8 terms, is equal to 8 over 2 times a. Now remember, the third term is your first term. So this 19 is your a value. Plus 8 minus 1 times your difference. Our difference, we've got the pattern, but we can also tell what our difference is by the coefficient of k, but you can see you're adding 5 each time, and so times 5. So guys, nothing tricky here. Just because we're not starting at 1 doesn't mean we change the way we do things. We do things exactly the same. We just need to be more mindful of where we start. So I'll give you a second to substitute that in, and then we will see what our sum is. So tell me what the sum of these 8 terms is. Oops. Nice, Ukizwa. You are indeed correct. Well done.
Ma'am,
Yes.
ma'am, do we get marks for showing our substitution? Is
In
it
terms of
necessary?
the substitution into the sum formula.
To get some 3, some 4.
So no, where you will get
Okay.
marks though is for the term. So you won't get marks for the
Okay.
actual substitution, but you get marks for the terms, yeah.
Okay, yes, ma'am.
And then guys, just on that question, you will get a mark for substituting into the sum formula. So please do show that, but you don't have to show the substitution for your terms. You can literally just go straight to the term value. That's fine. Okay, Zakis was the only one who's given me an answer. It is 292. That is the sum of these first 8 terms. But it's just through substitution we get that answer. The only things we need to remember is that A is not necessarily going to be where n equals 1 or k equals 1 or whatever equals 1. It's a first term of where you are starting. In this case, we started at term 3. Right, so take your screenshots and then we're going to have a look at another example like this, just with the geometric.
Ma'am,
Yes.
so do you see where it's k is equal to 3?
Yes.
Do you always then choose the consecutive following 2 terms like k is equal to 4 and then k is equal to 5?
Yeah, so remember, okay, the next example is going to go against what I'm about to say. But remember, n is always consecutive whole numbers. So term 1, 2, 3, 4. If we're starting at 3, it'll be 3, 4, 5, 6, etc., etc. But yeah, consecutive integers.
Okay, thank you, ma'am.
Good. Okay, like I say, guys, the next example is going to go against what I've just said, but it's fine. And I'll explain why it's fine now as we look at it. So if we have a look at this example B, why I'm saying it goes against everything I've just said is because k is now -2. Now we know that k should always be, or the term position should always be a natural number. 1, 2, 3, 4, 5, 6, etc., etc. So sorry, came out of nowhere. I do apologize. Excuse me. So this sort of is illogical to us because we know that n should be anywhere from 1 up, only natural numbers. But what we also need to bear in mind is even though we start from term 1, any pattern could be extended to negative infinity. We don't work with n is negative integers, but the pattern could be extended backwards to find terms that deal with negative integers. We just don't work with them. If you think of like a parabola, right? Most of the time when we talk about a parabola in terms of a number pattern, we're just working with one arm or one part of that parabola. But that parabola can extend both ways, same as a straight line. We're just looking at a portion of our straight line when it comes to number patterns. But that line can be extended all the way to positive or negative infinity. So whilst logically we want to fight this, we don't have to because it is possible. We just don't work with it in our syllabus. All right, so going off what Kirsten's question was, all we need to do here is we need to substitute in k is -2, k is -1, k is 0. We'll just keep increasing by 1 each time, and we will get the first 3 terms that we want. So if we substitute in all of those values, we get that our first 3 terms are 2 plus 6 plus 18, and so we keep adding. So we should also know that we've got a geometric pattern because of this exponent here. But obviously, if you're not too convinced, once you've got your first 3 terms, you can go and double check what's happening. I'm adding 4, then I'm adding 12. So it's definitely not linear. It's definitely not quadratic. So if I find r, 6 over 2, r is equal to 3. So I've got my r value. In this case, it does match up because this k is positive. If it was a negative k, it would need to be a fraction like I explained earlier. All right, but we have everything we need. We know what our a value is. We know what our r value is. And so we can go work out our sum. Sum of n terms of a geometric pattern is a times r to the power n minus 1 all over r minus 1. Now, the only bit of information I am missing is how many terms I am adding. So remember, n is top, so 6, minus bottom, minus -2, plus 1. Remember, whenever we have this negative situation, it's actually a positive. So we've got 6 plus 2 plus 1, which is 9 terms. Makes sense. I'm going from -2 to positive 6. It should be more than 6. So I want the sum of 9 terms now. And I substitute in what I know. A is 2. Remember to use your brackets when you substitute. So r is 3 to the power 9 minus 1 all over 3 minus 1. So I'll give you a second or two. Tell me what the sum of these 9 terms are. Just substitute it into your calculator. And remember, the series just keeps getting bigger and bigger and bigger and bigger. So it should be quite a large sum that you're dealing with. And you see, just double check your substitution for me. So make sure you've typed it in as I've written it over here. I'm going to double check my own substitution as well, just in case. You never know. So you saw I got the same thing as you. I'm just double checking myself. Nice. All right, so guys, exactly. Your sum is 19,682. Just double check your substitution, like I say, if you didn't get that. So make sure you have substituted incorrectly. And remember, the -1 is not part of the exponent in this formula is r to the power n and then separate term minus 1. Right, good. Let's take a screenshot of this. Alrighty guys, so like I said, on Wednesday, we're going to have a look at some exam type questions so you can see exactly how Sigma questions are asked, because like I say, this is often the more complex, I don't want to say problem solving because it's not really problem solving type questions, but they are the slightly harder questions. But once you actually delve into what is Sigma, what does it mean, those questions do become a lot easier. So we're going to have a look at that on Wednesday. And then as of next week, we're moving on to our next topic, which is functions. And as you always see, I'm going to come back to this now in a second. Right at the beginning of the lesson, I literally say here, you need to revise your grade 11 work, especially functions, blah, 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 blah. Functions, most of your functions questions in your exam is actually grade 11 type functions. So we are going to have a look at revision of grade 11 functions, but then we'll get into the matric work. But like grade 11 functions, you need to be revising it. Right, guys, but once you've got your screenshots and once you've got what you need, you're more than welcome to log off.